carry power from generating stations to the load centers, and they usually are long distance lines. They can be made as well as short lines. However, mostly transmission system, particularly at extra high voltage level, that occurs to transfer power in a longer length usually. So herein I will be presenting 3 case studies which has been done for a transmission system, which includes IEEE 9 bus system, IEEE 14 bus system, and a real Chhattisgarh state 400 kV transmission system. And then I will move towards the microgrid fault detection scheme, wherein I will present a case study on IEC microgrid. Then dealing with the distribution systems. The main task in distribution system, as the line is usually short, it may be within a periphery of 20 to 25 kilometers in a town. So the main task will be more crucial towards fault detection and classification, and there are few works which deals with location as well. And in this we will present a case studies of IEEE 13 bus 33 bus system, wherein specific solar and wind based distributed generators are integrated to the distribution network. And another case studies wherein the distributed generator should be placed at which particular bus, that DG placement solution is also presented. And the last case studies followed by conclusion and few publication and references. So I suppose that herein the participants are basically the PG and PhD or the faculty members. Rahul, am I correct?
Yeah, PG, yeah, equal professional and students, ma'am.
Okay, so obviously all have already studied about the power system protection scheme. So what is actually the basically need of power system network? So it basically ensures that the continuous and a reliable power supply is provided to the different loads, and that can be done by providing fast and accurate fault detection and isolation techniques. So the protective relaying functions are basically first to detect the fault. So it used to identify quickly the presence of fault, and once the fault is detected, we need to isolate the faulty part from the healthy part, and so that's to minimize the overall damage to the equipments, basically due to high impact of fault current that may cause the damage of insulations, particularly to the transformers and also the insulators. So these are basically the functions. So, and importance to prevent the damage and ensure the system reliability, and finally to maintain a power quality. And basically the main impact is if fault occurs in a system, so it will cause power outage. So we want that the duration of power outage should be reduced. So for that we must be able to detect the fault as fast as possible, and finally isolate the faulty part from the healthy part, so that the power can be resumed. Power restoration can be done as early as possible, and it will also ensure the safety and the impact of DG integration. We all know that the renewable energy sources, which are nowadays most widely used, and they are usually integrated at low voltage level. It provides an alternative solutions to the depleting fossil fuels, and also clean energy solutions, which is the basic requirement as per the main goal of sustainable development. So we need strive for this. So in power system network, if we consider different types of components that are there, so we see that particularly the overhead transmission lines, they are the major culprit, because they are exposed to the atmospheric conditions, vagaries of atmospheric conditions, the extreme weather conditions, and also the lightning, particularly lightning over voltage. That is the main main cause of the faults in the transmission lines. And then there is 12% in case of CT, CVT relay, 10% is your transformers, and underground cables 12%, and then switch gears and CVT. So different components that cause the overall faults that usually occur. So you can see that transmission lines are basically transmission or overhead lines, you can say, which is both transmission as well as distribution lines, which are overhead. They are the major wherein the fault occurs. So power system network basically starts with the generating stations. Generating stations in India, we are more having the thermal power stations, and also in few places in southern side there are nuclear power stations. So we generate the power, and through a power transformer, which is usually a step up transformer, we step up the voltage to a HV voltage level. Usually the EHV voltage level is at 132 kV and above, 132 kV, 220 kV, 400 or 765 kV. These are the voltage level that are available. In India, there is also 1200 kV voltage level situated. There is a short line project that is established at Bina, which is a joint venture among the different power companies, particularly you can say the ABB, Siemens, or the manufacturers BHEL, and they have done a joint venture to construct that 1200 kV initial line for very short length. And as far as all equipments are not being actually utilized at that voltage level, so it is a demo project usually, and that will give you the you can say ultra high voltage transmission lines. So once we get overall functioning of that as successful, so we will be seeing more ultra high voltage transmission lines in future. So you can see as the after generating stations, through power transformer, EHV lines are there, and through transmission towers, the transmission power is transmitted from generating stations towards the load centers. So they are you can considered as a substation, and then in substations it is further stepped down and transferred to the different substations which are nearer to the load centers, particularly the domestic one or the industrial one. So it can be further used either by for the residential purpose, or it can also be used in the commercial or industrial use. So these all will be your distribution lines. Before to that will be your EHV line. Now the DG play an important role, as I told. So these distributed generators, based on their capacities, particularly if they are of high capacities, they can be integrated at EHV distribution voltage level as well. But usually the rooftop one, or in Chhattisgarh particularly, we have DGs which are integrated at EHV level as well, particularly at 33 kV. So 33 kV is considered to be high voltage distribution, and LV distribution is the residential voltage value, that is 220 volt, the single phase, wherein rooftop solar units are integrated. And you can say that these DGs can directly feed to the local loads through the distribution networks. And main advantage of DGs is that they provides the clean, and the losses that may occur if these DGs were placed at the central point, the transmission losses will be avoided in this case. So that is major good thing that DG plays when we integrate DG at the distribution voltage level. So now transmission towers at this picture shows, basically it's a double circuit transmission lines, And usually single circuit lines earlier were used, but nowadays all towers which are constructed, they are of double circuit lines. So as from the same right of way, we can have the more power transfer capability. Usually with double circuit line, it is double the power from the same right of way. And they used to carry electrical energy from power plant generating stations to the load centers, and it facilitates the efficient and reliable power transfer from one place to another, particularly through over long distances. And energy transport and grid connectivity, they form the major backbone of this. And but due to exposed to atmospheric conditions, they are subjected to faults. And particularly fault causes are either due to short circuit, thundering, or storms and bird strikes.
Please मुझे to copy ना कर दूँ.
Somebody is unmuted. Please mute yourself so that there is no interruption in between. Then come
Yeah,
why we need a transmission line protection. So the main protection challenges are basically to provide the different protective relaying functions. That is, first is the fault detection, fault classification, and location estimation. And also under dynamic operating conditions, the system should be stable. That is, if the system is subjected to varying load conditions or varying generation patterns, particularly through DGs, which are highly intermittent, and network reconfiguration. If such cases appears, then the protection scheme should not deal all these cases as faulty, because they are the dynamic operating conditions in which the system is subjected to. So the protective railing scheme should consider them as healthy conditions in general. And reliability and the non-faulty transients, particularly like power swing and switching events. So these two events are basically the main reason behind the blackouts that has occurred in India, particularly in the year 2013. And so power swing, basically it needs to distinguish among the normal power swing and the actual faulty condition to avoid the unnecessary tripping of the distance relays. And switching events, like when you switch heavy loads, or when the capacitor banks are switched in, or reactor banks are switched in or out, so they may pose protection challenges. And the reliability of the protection scheme is to be maintained under these non-faulty transient events. So similar way in distribution systems, the main challenge is the intermittent nature of the DGs. The nature of the DGs, particularly if they are solar based DGs or wind based DGs, and whether they are producing a localized power in general, and they uh, give you major advantage towards the thermal or nuclear power stations by producing the localized generations, and reducing the transmission loss, avoiding the transmission loss, you can say. And with renewable integrations, it will facilitate the greener energy, and the carbon emission will be zero in this case. So we should know about which particular type of DGs or the generating stations, particularly the solar or wind, how at what voltage level they are integrated. So this slide shows the main integration of DGs at different voltage levels. So the individual photovoltaic panels, that is the rooftop panels that we are having at individual homes, they are usually integrated at low voltage distribution grid. So you can consider it to be at 230 to 415 volts. At this voltage level, they are integrated. Then comes between 11 to 66 kV. It is considered to be a medium voltage distribution grid. Herein we can integrate different types of small scale hydro power plants or biomass based power plants, tidal wave systems, and small industrial combined heat power plants, they type. All these are integrated at 11 kV and 66 kV. Then if you at a high voltage distribution grids, which ranges between 66 to 132 kV. Herein we integrate the offshore wind parks and large scale hydro plants, similarly large scale solar plants as well, and large scale industrial combined heat power plant. And the thermal power plants usually are integrated at 132 kV and above. So large power plants, particularly of larger capacity, so it will be integrated at 132 kV level. So that shows your in terms of particular voltage level. And if you see herein, so this is a typical power system model wherein we have integrated DGs at different places. You can see, so generating station, transmission systems which carry power through transmission line, then comes the distribution system. In between will be the power transformer and the distribution transformer. Power transformer will step up and this will do step down. And so PV generating can be integrated at distribution voltage level. In also there are energy storage system in India. If you come sometimes in Chhattisgarh, there is one battery energy storage system based solar power plant which is basically installed in Mahasamund, Chhattisgarh, the district Mahasamund, Chhattisgarh, by Solar Energy Corporation of India Limited. It is of basically 40 megawatt and 120 kVA. That is for 3 hours it can supply 40 megawatt of supply. So that way the power stations which includes energy storage system also are there, and the wind turbines, reciprocating engines. So these types of DGs are also installed at distribution system level. Now what actually happens when we integrate DGs in the system? So this can be considered through a simple network shown herein. If you consider this is your grid, and in between is a transformer, and then between two buses it will be basically a three-phase transmission system. And you can see that at different points there are load centers. So if their loads is connected, so it will be basically a substation wherein loads are connected, and loads will be through a step down transformer in particular. So for example, if you consider a fault at point A, so the fault current IF will also be supplied through grid, and also the DG will be contributing the fault current at point A. But the measurement that the relay at bus B2 measures only the grid current that is flowing in this through the CT. It does not measures the amount of fault current contributed by DG. So in this way, basically the fault detection may be not correct, or the underreach may happen in the relaying scheme. Also the fault current reverse condition that may occur. So particularly the earlier systems, they were radial systems, distribution system in particular, but with the integration of DGs the system is no more a radial system. So the conventional protection schemes will maloperate in this condition. Then the different DGs that we are integrating, this is using the power converter circuits, because usually says if solar DG is there, so that will generate the voltage in DC, which is further through power electronics converter, particularly operating as inverter, they will be converting DC to AC to integrate it with the AC system. So there may be fault conditions in power electronics converter as well, and high overcurrent protection schemes may fail to detect. And if the system is subjected to high impedance fault conditions, this is very crucial type of fault, wherein due to the high impedance nature of the particularly ground types of fault, the current amount, the faulty current amount is not considerably high. So that may come in the range of, you can say, the normal overloading that may happen till 10 to 20%. So So it may be remain undetected if a high impedance fault occurs to the conventional scheme. So all these are the major protection challenges that you need to take into account while designing any protective relaying schemes for the transmission and distribution system with integration of DGs. So that way we will be discussing more in detail in the coming slides. So there is a very, I have placed one simple short review wherein different schemes that are developed for fault detection and classification and distribution system for transmission lines, detection classification schemes, and lastly the location schemes and also the DG placement. So a short survey was being done and uh, several remarks that are shown herein, which are you can say considered as the main motivations, which are the research gap that are there in the existing literature, which will be considered to be overcome in the new schemes that will be proposed in detail. So research gaps herein we considered as the renewable energy oversight, wherein previous research neglects the impacts of renewable energy on the power system, and traditional fault detection schemes, therein the real-time challenge in fault detection schemes is there, and location schemes wherein high impedance faults are not be able to detect and locate it correctly, and simply the distribution system also, earlier systems, they does not take into account the DGs into as a part of their network. And finally, real-time validation of the schemes are not being done earlier, and for non-faulty transient events, the previous studies does not take into account the performance investigation, because this is the conditions wherein the system should not consider it to be a faulty condition. So these will be the research objectives that will be dealt in this, wherein we will be initially modeling the standard test system of high voltage and distribution systems with penetration of renewable energy system in either MATLAB or PSCAD, and then through the short circuit studies, the different faulty situations that will be simulated, and these schemes will be further utilized to generate the training data set for the AI based schemes, and detection and classification techniques using artificial intelligence schemes will be developed for distribution and transmission systems, and the reliability of the proposed schemes will be checked under various non-faulty and faulty events, and finally real-time analysis for the Chhattisgarh state power transmission system will be done. So I will start with the first AI based scheme, that is the fuzzy logic based, wherein the high impedance fault detection in DG integrated distribution system will be discussed. So what is fuzzy logic? Fuzzy logic is basically logic which is not, you can consider it to be in between true and false. There is a partial truth that exists. So wherein the system is subjected to imprecision or uncertainty, fuzzy logic is basically considered to be a ideal solution for having the ambiguity to be solved. Herein, this fuzzy logic was proposed by the scientist Lofty A. Jade, and he gave that if the system is subjected to fault, how can a fuzzy logic can be introduced in this as a scheme to detect the presence of fault in the power transmission system. So basically fuzzy logic works initially by converting the crisp input variable values into a fuzzy variable through a fuzzification system. Then there will be a rule base wherein the input variables and the output variables will be clubbed in through if then rules, and all rules will be aggregated, and fuzzy inference engine will finally give you the overall output results through these fuzzifications, and causing you the protective relaying functions for the transmission system. Here in fuzzy logic system, we don't require any training module, as in case of either artificial neural network or any training based uh, AI based model like KNN, net based classifier, or any SVM. All these are training based method, but fuzzy logic is basically not a training based method. It offers a high speed and ease of implementation and interpretability, and also gives a trade-off between precision and significance. So there are two type of FIS that can be used: Mamdani type of fuzzy inference system and Sujano type of fuzzy inference system. And in Mamdani, we employ the linguistic rules and fuzzy sets to map the input with the output using a fuzzy logic reasoning, and their adaptability to fluctuating and fault current and voltage values make them well suited for the fault detection and classification task. Then in Sujano type, herein we use the linear functions for the output membership values, and which provides a crisp output based on the weighted sum of the input. So both of them will be utilized in the coming slide for fault detection and classification. So this is basically a flow chart how we will apply a fuzzy logic system. So we will be initially measuring the fault current signals at the relaying bus. Then so we get a three-phase current signals. In addition to three-phase current signal, using sequence analyzer, we calculate the zero sequence component of the current. This is required for presence of ground in the fault loop or not. So ground detection is done through the zero sequence component, and which of the phase is faulty, from them the three-phase currents can be utilized. So in fuzzy logic, we have before the current signals are not directly taken as input, the specific features of current signals have been calculated using discrete Fourier transform, and we calculated the approximate coefficients of the three-phase current signal, and then applied a standard deviation. The standard deviation is a mathematical calculation expression wherein we can calculate the standard deviation of the DWT coefficient of the three-phase currents, and we compare it either through a threshold or through a fuzzy logic system. So there are two types of schemes: either directly the standard deviation feature can be controlled through threshold, or also we can compare it, we can give these as the feature as input to the fuzzy logic system, wherein the fuzzy logic based fault detector and classifier is initially designed based on different phases. Each phase wise separate FIS module have been designed, and ground FIS is also designed. To total four FIS has been designed, and using an OR gate, either of the phase, if is it faulty, so that gives the presence of fault, and the combination of all them outputs can give you the fault classification, that which of the type of fault has occurred, whether it is single line to ground fault, double line to ground fault, or face-to-face fault, or triple line to ground fault. So all these can give you the fault classification output as well, in addition to detection. So simultaneously we get fault detection as well as classification through the 4 FIS module. So to test this scheme, we have chosen the IEEE 13 bus system. So this is overall IEEE 13 bus system. Here in the utility grid is there through transformer, and we create faults at between the bus 650 to 651, and this is the location wherein different types of faults at various locations have been simulated. So in this distribution system, you can see that there is wind farms, battery energy storage system, solar PV or PV module or solar based DGs, as well as diesel generator. So this type of system, here in the overall wind power capacity is of 1.5 megawatt, solar power module is of 0.3 megawatt, and diesel generator is of 3.125 megavolt ampere, and battery energy storage system is given as the capacity of 200 kilowatt hour. So overall modeling of this system is done in MATLAB Simulink. So now how the feature has been extracted, as I told, I have applied discrete wavelet transform. So the simple three-phase currents that are initially discretized using the sample and hold. So here in for 1 millisecond each samples are, so we can get 1 kilohertz as the sampling frequency, and the moving window wherein the 20 samples are taken and the moving window is shifted sample by sample to calculate the discrete wavelet transform. So this moving window for from one cycle, if we have an approximate coefficient of them has been calculated, and then finally we obtain a single value using standard deviation. Now once this one single value is obtained, the window is shifted to by one sample. So as we shift it by sample, the number of samples that we obtain by shifting the window is increased. And say for example, so in this case the current feature that we have taken as input to fuzzy logic is standard deviation of the approximate coefficient of the three phase voltages and currents. So you can see that if the faulty phase, if this is a particular case of fault wherein the dB wavelet, Dobitchi wavelet has been used, dB1, and the feature, that is the standard deviation feature, has been shown in this figure. You can see up till the there is no fault, the system is having a lower value of feature, and as the fault presence at this point 3, the fault has been incepted. So the there is change in the nature of the feature vector, and particularly dB1 we have seen it for all Dobitchi's, dB2, 3, 4, 8 and dB12. So this dB1 is the giving you the clear picture of presence of fault, so that has been taken as an input features for detection of fault. Now how we design fuzzy logic modules. So three fault detection modules we have designed for each phase current, and then fuzzy logic controller, both Sujno and Mamdani type has been used, and current features are divided into 4 ranges, and input triangular membership functions we have used as SD1 to SD4, and based on these ranges, and then Mamdani type of architecture has been used, and finally the min max decomposition technique has been used. And how to map these input features with the output, we want that the system should detect the presence of fault, so it can be either output should be either low or output should be high based on the presence of fault. So there are only two output membership function, th, that is t high, and t low, target high, target low, and based on the SD value in different ranges, we consider it to be T low in SD1 and SD3, and SD2 is T high, and SD4 is also T high. So this way the threshold based membership functions have been decided. So all this the same thing is represented here, wherein the either Mamdani or Sujno type has been used. 4 type of ranges have been used for the input function based on the SD value of them, and they have been mapped with the target low and target high output using this type of rules. So now once the fuzzy logic has been designed, now the main step is to investigate the performance of the design system. So herein we have considered an AG fault and with different irradiance value. Normally we consider to be the 1000 watt per meter square as the solar irradiance during the midday hour, but it may reduce either in evening or in morning hours. So we have checked the performance using irradiance value as different 800 watt per meter square, and temperature is T equal to 40 degrees Celsius. So this is the 3-phase current, and there is a AG fault. So you can see the A phase current is slightly higher as compared to B and C. And through the feature vector, if we check it, so phase A feature vector is changed, and with this FIS output is able to detect the presence of fault in 4.2 millisecond time. Similarly, the Mamdani and Sujno both are able to detect the presence of fault in very less time. So this is in second. So if I consider to be in millisecond, it is 4.2 millisecond, 2.5 or 7.5. So it is quite less, usually within quarter cycle. So the system is very fast. So that was for one case. Now we have also checked it, the performance for different types of high impedance and low impedance fault with varying wind speed. Say for wind speed, the wind DG that is herein, it may have be subjected to different wind speeds. So if wind speed is changed, how the fault detection time changes, that is shown in this slide. So it can be seen that even if the wind speed changes, then also the performance of the scheme is not disrupted. It is able to detect the presence of fault in very less time, in 2.5, and here in 3.3 millisecond time. Then comes the another case of that is an evolving fault. What is an evolving fault? Evolving fault starts with the initiation of one type of fault at any instant and converting it to another type of fault. It usually happens when one of the conductor falls on the ground, and due to the overall weight of one of the conductor, that finally causes the other conductor in the tower to also come down to ground. It may happen either also due to tree branch touching the phase conductors. So evolving faults occurs, and we need to detect the presence of those type of faults after certain one inception time. So there will be two inception time. Initially will be one type of fault, and then it will be converted into another type of fault. So in this case also, the scheme correctly detects the presence of fault. Now I have also told in previous slides that we should investigate the performance of the scheme under non-faulty conditions, like switching events or load switching. Say for example, 36 kilowatt induction motor load is connected near bus 632, and it is switched into the system at 0.3 second, and then it is disconnected at 0.36 second. So how does the system behave, and whether the system is considering it to be a faulty condition or not? So you can see from the results that the output is low throughout. So it confirms that this condition is considered to be non-faulty. So that is causing its reliability. Similarly, DG switching, when we switched in different types of DGs, so how does relay scheme should not detect that type of as a fault? So it happens basically solar or wind-based DGs, they are intermittent based on the cloudy nature. If the particular solar power plant's location, so that may not be delivering power to the grid, and in some other time when there is clear weather, so it will be delivering the power. So in this way the DG may be switched in or out, but that should not be considered as a faulty situation. Further effect of noise is to be considered. So to check that, we have inserted 30 dB noise in the phase current signals and checked the performance of the scheme with and without noise. So it is correctly able to detect the presence of fault. So in this chapter, we have designed a combined discrete wavelet, transform and fuzzy inference based system for fault detection and classification in distribution system, which is integrated with DG. And both high impedance and low impedance faults have been discussed. The system that is used to test is IEEE 13 bus system. Impact of various DG switching events and noise has been considered, and the scheme is able to distinguish between the different conditions. Another non-faulty may be transformer energization, capacitor bank switching, or load switching. So all these have been correctly distinguished, and evolving faults have also been discussed. So that was the summary of the first one. I hope that you could get the idea behind how to apply the scheme. Now I will move on to the next type of protective relaying scheme, which is a resilient protection scheme for common shunt faults and high impedance fault in distribution line using wavelet transform. So herein discrete wavelet transform has been used, and herein main thing is to use it only DWT. So it is a threshold based protection scheme wherein we will be deciding the threshold functions, different threshold functions to distinguish between non-faulty and faulty events, and fault among faulty, whether it is a low impedance fault or a high impedance fault, that will be decided. So how the scheme works: we take the three-phase current signal, extract the samples through a moving cycle of one window, then we apply wavelet and extraction of wavelet coefficients and computation of standard deviation of the feature, and finally with the fault detection criteria as per equation 8 in the figure, that is done, and it is compared with the threshold value. So if it is less than T1, it is considered to be non-faulty or switching event. If not, then it will check it whether it is greater than T1 and less than T2. If yes, so it will be an high impedance fault, and if it does not satisfy these two conditions, then further it is checked whether it is greater than T2 and less than T3. If yes, then this is a no fault oblique switching event, and if it is greater than T3, then it will be a normal shunt fault, that is a low impedance fault. So if it is a presence of low impedance fault, so individual phase currents will be studied to detect the presence of fault in individual phases, as well as ground will be studied to have a threshold function greater than T4, and accordingly fault classification output will be proposed. So we will see how it works. The main thing is to check out how the threshold functions is decided. So herein we see that for a low impedance or a high impedance fault, for low impedance fault, if it is greater than T3, so that they all are considered to be a low impedance shunt faults. But if there is no no low impedance fault, rather if it is a high impedance fault, in that case it is to be checked whether the it is the phase currents feature vector is less than T1. Then if yes, then it will be a non-faulty event, but if it is greater than T1 but less than T2, so HIF will be confirmed. So all this schemes which I discussed in previous slide, it is same here in text format. And different fault cases that have been studied is by varying the value of fault resistance, different types of faults, all 10 types of faults have been considered at different locations. So it will be 1/4, half and 3/4 of the length, and with varying fault resistance value between 40 to 150 ohms, different types of faults. And herein you see that in shunt faults we consider the phase to phase fault as well, but in high impedance fault the only ground faults have been considered. Then the switching events wherein all non-faulty events are being considered. And to detect the presence of fault, at what time the fault has been detected, so we simply from fault inception time, the detection time is subtracted to give the overall fault response time of the scheme. So you can see that in this case, the three-phase current wherein in AG fault is incepted at 0.3, and output of fault classification, you can see that this is for all three phases and ground. So A and G goes high, B and C remains low. So it confirms the presence of AG fault in this system. Now, in case of high impedance fault, you can see that the presence of high impedance fault is detected at later duration as compared to that of low impedance fault. It is due to the nature from the figure of the current. Can you identify the presence of fault? It is quite difficult to identify the presence of fault, particularly high impedance fault, from looking into the figure. But if we check out the feature vector that is used to identify the, so it gives you the changes that the input feature value changes after the presence of fault. So fault detection output is high, and particular phase which is faulty, that is also detected correctly. So in this way, we can provide both low impedance and high impedance fault detection. Now, in case of switching events, so if DG is switched in, so you can see that if DG is switched in, so the current value that increases, okay, and the phase input phase vector that also increases, but it is well below the threshold that has been decided for DG switching. So fault detection output remains low throughout. So this confirms the reliability of the scheme during DG switching events. Then the scheme is also tested for islanding mode of operation, wherein the grid has been disconnected and only DGs are feeding to the loads directly. And herein we check the different normal shunt faults. So it is able to correctly identify the presence of shunt faults in islanded mode of operation as well. So that gives the another performance criteria. Now, in case of inverse power flow, if the power flow current that reverses suddenly, so that happens particularly when the current flowing in one particular direction normally, and in case of fault the current reverses. So how the, in case of say for example, if grid is disconnected and power is flowing through DGs in other directions, so that way it should not be considered as a faulty one. So fault detection output is not high in this case. And in case of load switching also, it should not be high. If load is only switched in or out, so system should not consider it to be a faulty situation. Fault detection output should be low throughout. So the condition is satisfied in this case also. Now finally, the scheme has been validated through the Chhattisgarh State Electricity Board network, wherein the fault data that has been recorded through DFR, particularly on 14th March 2016 at this time interval. And this is the SEL relay software, that is WaveWin, which is used to capture the three-phase voltage, neutral voltage, and these are the three-phase currents and the neutral currents. So from this we can consider that which phase is actually faulty. So IA phase has been considered to be faulty. You can see that this phase is faulty. B and C remains almost equal to the previous one, but A phase current suddenly increases. So output detected by proposed scheme is confirming that the fault is present in the A phase. And other events have also been checked, and it correctly identified the fault type, and the fault detection times are shown in millisecond in this case. And we have also compared the proposed scheme with the SEL 751 type of relay, whether it is able to detect the fault. Yes, both the relays are able to detect. Switching events detection is also done. Herein communication infrastructure requirement is there in SEL relay, but in proposed scheme it is not required. And data acquisition rate in SEL relay is 32 samples per cycle, but for proposed scheme is 20 cycles. And fault detection time ranges between 1564 to 180 cycles, wherein in this case it ranges from 1 cycle to maximum 5 cycles time. So finally comes to the summary, wherein in this scheme we have proposed the wavelet decomposition based method for fault detection and faulty phase identification of distribution line system. Standard deviation feature of the approximate coefficient have been calculated using a recursive moving window of 20 sample, and SD feature is compared with the preset threshold value to identify the presence of high impedance fault or common shunt fault, or distinguish these faulty events from the switching events. The system is validated in IEEE 13 bus system with solar and wind based DGs, and it effectively discriminates among all types of faults and switching events. System is robust for against non-faulty switching events, and it is also applicable in an islanding mode of operations. So this way we cover the two schemes herein. Rahul, do I have more time to discuss?
You can take, ma'am, as per your convenience, ma'am.
It's
But
8
the
to 9
participants are less. That's no
are
issues.
there. Okay, so another 10 minutes I will take them, no problem. And after that, a few questions I can take from the students. Meanwhile, you can also post your any query in the chat box. I will check it at the end.
Yeah.
Okay. Then the last scheme that I'm discussing herein is advanced deep learning based methods for efficient distribution system management and for fault detection. So particularly management of DGs is considered to as one of the main tasks is the optimal placement of the DG. So we want that the power quality should be enhanced, overall loss should be reduced, and reliability of the system should be improved, and it should be resilient, and the efficiency should be increased. So these are will be the main objectives to discuss this. IEEE 33 bus system has been utilized, and it contains 12.66 kV distribution network system with 33 bus, overall 32 distribution lines, and there are 5 switchable lines. Total power drawn is 3.715 megawatt, and reactive power drawn is 2.3 MVAR, and voltage limits between 0.9 to 1.1 per unit. So to finally get the idea that at which bus the DG should be placed, we have utilized the reinforcement learning algorithm, and this algorithm will give you the overall uh, placement of DG at which bus will cause improvement in the overall voltage profile and reduction in the loss. So from these figures you can see that the reinforcement learning training process is shown herein, and from the voltage profile there are two figures, one is without DG and one is with DG. So you can see that without DG the value of sorry, this is blue one, this dark one, the value of voltage profile was fluctuating more as compared to when the DGs are placed. So you can see that the voltage profile becomes almost flat as compared to the without DG one. So this way the voltage profile improvement has been obtained through reinforcement learning. And once the DG placement is fixed, now we use the in 33 kV system, we calculate the three-phase RMS voltage and currents, and they are utilized through phasor measurement units, which are located at different buses, particularly at 3, 4, 8, 11, 15, 26, and 31. These are the bus wherein the PMUs are located, and through remote terminal unit, the three-phase voltage and current signals, they are being transferred through communication network at the main point of common coupling, and we get the three-phase data available at one point. And we have considered here in different types of fault situations, both high impedance and low impedance fault with different values of resistances. And for high impedance fault, we have considered the concrete surface, soil, and concrete with soil both as the faulty surface, and LIF range is between 0 to 40 ohm, and fault location we consider at different buses, and there are total 6 fault inception angle that we have considered, and some non-fault scenarios herein we considered. Another is the non-linear load switching, and another is the motor load switching, and DG tripping, load switching through capacitor in and out. All these have been considered. So now once all this data set has been generated, fault detection is done through deep learning network, which is the hybrid CNN and LSTM model, and attention based one dimensional CNN and LSTM model is utilized. The parameters of the network models are shown herein. Performance of the design model is studied by the different confusion matrix parameters, and the formula through the confusion matrix to determine accuracy, dependability, security, and overall detection times are shown in this slide. From there we can see that once the network is designed, so the accuracy is near to 0.98 around, and the training loss figure is shown herein, and the dependability and security you can see from different network, only CNN, then CNN plus LSTM, and lastly is CNN LSTM plus attention mechanism. So this gives you more improvement. With this we get 100% all faults to be classified correctly. So performance has been investigated for both low impedance and high impedance fault, and fault detection times for different types of fault are shown in this figure, which is in milliseconds. For non-faulty events, the fault detection outputs remains low, and it is also evaluated for another scheme as a microgrid system, wherein the IEC 61850-7-420 is considered herein. The same system, initially it was designed for some other, but if we test it for other system, then also the fault detection output is correctly detecting it. So the overall system accuracy and classification modules are illustrated herein. So accuracy is for non-faulty event is 1, that is 100%, and for faulty events you can see herein average accuracies remain 98 point something. So in this we have proposed the reinforcement learning based scheme for placement of DGs, and IEEE 33 bus radar system has been utilized. It is used to detect and classify the faults in presence of DG, and used to test for both low impedance and high impedance fault, and also for non-faulty events. And the scheme is also test for microgrid test system as well. And reliability has been compared with other deep learning algorithms, that is only CNN, only LSTM, and combined all three. So this way it gives you the overall I will show few of the publications and final conclusion. What else you can do? I would suggest you to work for more complex power system network. The real power system network, if you get the data set for that, then simulation of such systems can be done using MATLAB or PSCAD system and validated in that. Then also you can validate the schemes that you have developed in OpalRT for real-time validation, and performance analysis for actual high impedance fault data set. So real fault, HIF type of fault data records have not been found through the state electricity board, but it can also be done. And further works can be carried out on DG integration and transmission system also. More advanced deep learning architecture like transformer models can be investigated, and to overall fault localization decision, that is also one of the fact that can be done. And these are the few of the journal publications that have been carried out at NIT Raipur. The PhD scholar Manvi Bhatnagar published all these papers under my guidance and supervision. So she has recently completed her PhD, and these are few of the conference paper. So paper should be communicated to any of the SCI general in general, and general impact factor is major concern that you should take into account while submitting the paper. And these are few of the references. Thank you. Now I am open for any query that you need to.
Yeah. Well, let's take it, Solution ma'am, for the three sections. Uh, I would like to invite any queries regarding this particular presentation. Oh, check your Google Scholar profile also here.
I have a question.
Yeah, please.
Dr. Anamika, are you actively involved in the research related to the AI applications in power system protection. Are you
Yes.
doing any active research on that?
Yes, actively I am doing. There are around 7 to 8 research scholars under my supervision at NIT Raipur who are working in the area of AI-based scheme for power system network.
Okay, I'm interested to know more about your research. Is that a way I can contact you? Or
Yes, wait, I will send you my affiliation details wherein you can contact me. I am sending the link in chat. You can check it.
sure.
And
Also, the presentation was really good. Can you send the presentation slides as well?
yes, I will share that. soon.
Thank you.
Thank you, Sanju.
One more thing.
Yeah.
When we propose some AI or ML related things, we need power system data to train our models, right?
Right.
Where are we getting this data from?
Actually,
Do
for
you have
training
a
data, in general, through simulation of the power system network, different fault simulation studies had to be carried out to get that data. And
Okay.
once the data set is sufficiently available with you for training, so test data set also need to be generated, or you can test it with real captured data through the relay. Digital fault recorders are there in the transmission and distribution network installed. You can get the data from there and check it.
Okay. Okay, thank you. I was just curious to know because I found that that's the most difficult thing
Yes.
when we propose
For power
an AI
system
or
is
ML model.
particularly because it is more difficult, and for that only simulation studies are basically carried out.
Sure. Are you using any software like ETAP to generate the data or?
Right. There is ETAP, EMTP software also that is used.
Okay, yeah. Thank you.
Thank you, Sanju. Ma'am, actually, Sanjo is from Houston, so we already discussed the same thing regarding the power quality itself. Because we are dealing with more about the test cases from the MATLAB mathematical models in the power quality side.
Right.
Yeah,
Always
I'm
depend
from
on that
I'm
thing.
from the industry actually.
Okay, good.
Yeah.
I'm
So
from the
now, yeah.
industry, and I usually ask my doubt to Dr. Rahul. He's my go-to AI expert in power systems. So
Okay. Right.
yeah.
Yeah.
I
And
really appreciate this kind of efforts. I wish I could attend more of this kind of presentations. Thank you for organizing this presentation.
thank you, sir. Yeah, that's a point I want to mention like that. There are we can create something from the mathematical model itself. I mean mathematical test signals itself, but we couldn't find a exact power quality real time data, and it is even in the Power Globe also. Few days back, the same discussion going on with the real time. It is difficult in getting the real time data in power quality events. So, what's your opinion then to how to tackle it actually?
Power quality data you are asking basically, na? So actually, in terms of power quality, we need that what is the voltage profile, what is the frequency. So that will be the main fact. The active and reactive power delivered value. So recently we have got a consultancy project from state electricity distribution company, particularly to have the impact of solar integration on grid. So different systems wherein DG systems have been integrated to grid, and we need to study the impact of inverter rich DGs on the grid. So that is one of the major fact that gives you the real data of the existing system. If you are know to any of the state electricity board near to you, you can get involved with the working engineers there, and they will give you the system or the network configuration data. which you can simulate using any of the power system simulation software.
Yeah, but ma'am, the difficulty I think like that we can classify the proper events in that. So several events in the normal we have 15 classes or 17 classes are there, but for the real time case we can't expect that
Yes,
15 to 17 classes for the classification. Right?
right, right.
So
So for that only
uh,
simulation data is required. The real will be very less.
yeah, right.
Or even sometimes we need to analyze it through simulation software. The case studies, usually in concrete format, we get the fault records in concrete format, and we can visualize them to get which are the
Correct.
power quality events that has occurred.
Yeah, right, right, ma'am. And one more thing, okay, I want to ask like that. You already conveyed regarding uh, reinforcement learning side for the
Right.
protection. So those data sets are also created through EMPP, right? Or any
Yes.
other EMPP, right? Yeah. Okay.
Right.
Yeah. Okay. Thank you. Any other queries from the participants? Please unmute and ask because we are expecting a number of participants, but maybe the holiday it's a problem. I see. Yeah.
Hmm.
Yeah.
Okay, no
Yeah.
problem.
Any other queries? Okay, ma'am. We can because you are also for the tight schedule and lot of responsibilities in Raipur department also. So I know that. So yeah, thanks for coming for our humble platform, ma'am,
Okay,
and keep on supporting us too. And we will like support every privately activities there also. Yeah.
okay, okay, good. Thank you.
Thank you. Thank you. Thank you.